setting up so much of modern mathematics. So the interesting kind of idea or dichotomy that I introduced in a few videos back is that when you start off, when we're building up mathematics, capturing the same kind of orientation that we had in our very first video, but it's a little bit more sophisticated because now we're putting things in the multi-set framework. And we can now be more precise and say that NAT represents the type of natural numbers represented this way. So in this formulation of things, you have a natural number precisely when you've gone through the trouble of writing out an expression like this. And of course, the distinction between what we're doing now and the way we started the series is that now the empty multiset is going to be included as a possible natural number. If we're thinking about natural numbers as being M sets of marks, then it's possible to have an empty M set. And that empty M set we're going to call 0. So that's our distinguished zero object in our world of natural numbers now. So there's a distinction between the way we started the series where 0 was not included. Historically, 0 is not really a natural number, but with this sort of more modern point of view, we are including 0 in the natural numbers. So to summarize, the fundamental ingredients that we really have here, okay, in this setting up of natural numbers is the two concepts of nothing and something, represented by emptiness, nothing on the page, and represented by this mark, this unit something. Which doesn't have to be a straight line. It could be something else. It could be a circle or dot or something else, but it should be uniform, so they should all be something the same, and it should be something simple and something kind of fundamental and very easy to write down. And the other thing that we need, of course, are brackets. The brackets that we're using to denote multisets that contain our bunches of marks so that we know where they end. So they're bounded and we have control over where they actually are. And so we have these things called natural numbers, and here's some examples. So there's a natural number, there's a natural number, there's one, there's another one, there's another one, there's another one, and there's the empty set natural number. They're all natural numbers. Some of them might be the same. For example, this one here looks a lot like this one. And these are the same, but that's fine. Notice that there's not intrinsically necessarily an order to them at this point. It's a bit of a subtle issue, but we're just saying what a natural number is. We have not yet gone to the trouble of organizing them all in some kind of list or pattern. Okay? We've just identified what it means for an expression to be a natural number of type NAT. And let's compare this view to the 20th century view of natural numbers, which was reliant on a prior set theory, and posited that natural numbers were things that were cooked up from sets of sets of sets of such, basically starting with the empty set. So, for example, the number 4 was the set 0, 1, 2, 3, where 0 was the empty set, 1 was the set involving the empty set, 2 was the set consisting of 0 as well as 1, and 3 is the set, well, consisting of 0, 1, and 2. So, in the 20th century, the view was that the number 4 officially is this thing. Now, our view, which is a 21st century point of view, we're moving ahead here, is that the number 4 is represented by this. It's a multi-set which has these marks in it. I want you to compare these two things, all right? And objectively, scientifically, rationally, tell me which one is better. Which one corresponds naturally to the way people think about natural numbers? Which of these views do you think supports a more sensible notion of operations, addition, multiplication, proofs, etc.? Okay, so it's pretty clear what the answer is, of course. Let's have a look at equality. The idea of specifying when two expressions that we write down are actually equal. It's a very important notion. So we're going to have a look here. Here's the definition that two natural numbers are equal. Talk about that. Precisely when we can match up their entries. What do I mean by that? Well, here are two natural numbers. Here's a natural number, and there's a natural number. And the claim here is that these are equal. And what does it mean to be equal? Well, it means that we can match up the entries from this one with the entries from this one. So we match these and these are going to get matched up, and these are going to get matched up, and these are going to get matched up. You also do that sort of physically. These are matched up, and then these, and then these, and then these, and then this. Okay, so it's not very necessary to count them. You don't have to have a prior notion of counting to do this. Okay? We're just matching them up in the way that some primitive person might match up, 5 fingers with 5 X's on a piece of bark. Just match them up. Here we have a natural number which is not equal to this natural number. And the reason is when we try to match them up, say that match up with that one, and match this one with this one, and match this one with this one, well, then this one here does not match up with any one of there, so we can't match them up, and so these two are not equal. So So this is meant to be simple, right? This is meant to be a theory that a primary school student can understand and appreciate. You see, this is corresponding with something reasonable, something intuitive, something useful. Right, so now we come to a very important and interesting development. What happens when we look at addition of natural numbers? The simplest and most fundamental operation in some sense. Okay, so an interesting thing happens here, which again is probably going to go outside your natural intuition and experience. We're going to look at addition in a different way. So it's usually considered that addition is a binary operation. That almost goes without saying when we're starting to do arithmetic in the usual framework. For example, we said A plus B plus C. We have a number B, we have a number C. We're adding them together to get another number A. We start with two things, and we combine them, we get another number. But in the M-set framework, which is something that most modern students of mathematics are not that familiar with, in the M-set or multi-set framework, we have more flexibility. We can think a little bit bigger than we can, perhaps with other data structures. In particular, the multi-set framework is not ordered, naturally, and it's not constrained by just having one of everything. Right? So we can deal with multiplicities with M-sets, and we can deal with things not being ordered. That's the essential orientation. So that affects us when it comes to defining addition. So it turns out that in the M-set framework, having a binary operation is neither necessary nor desirable. What are we talking about here? Well, to add natural numbers, what we're going to do is we're going to form a new M-set containing all of the entries of the M-sets that we have. I want to show you this physically. Okay, so here's the box, the blue box, and in this blue box here we see a couple of little boxes or containers. So here's a container, it's got some coins in it. Okay, that's container number one. And then here's another container, it's got some more coins in it. And here's a third container, containing some more coins. Okay, so these are M-sets. Some multi-set of coins, there's some repetition, and they're not ordered. This is another M-set of coins, and here's another M-set of coins. So we have a couple of different M-sets of coins. And now I'm going to add them. I'm going to show you how to do this physically. I'm going to drop this. So I take this one, and this one, and this other one. Okay, I'm going to add them. But I'm going to do it in a non-binary fashion. Okay, I want to add them all together. Let's see if we can do this. Okay, three things in no particular order. Whoop, I just dropped one there. Pick that one up. Okay, there we are. Back on track here. Okay, we have three multi-sets. I'm now going to add them. Ready? Watch carefully. Okay, there's no more left in our containers. We have dumped everything out, as you can see, perhaps, and we have all the coins there in this new multi-set. We have added the three multi-sets together, but we have not done so in a binary way, right? We just dumped them all out. Independent of order. Independent of having to do two at once. First of all, we have lots of different containers. We're just dumping them all here. We have three people doing this. It's a lot easier. We also dump our individual containers into the M-set. We'd be adding the contents. So it's a very interesting, non-standard view of what addition is. So, for example, when we write stuff down, okay, here's an M-set of Marx, here's an M-set of Marx, here's an M-set of Marx, so we have three natural numbers in this case. And we're going to add these natural numbers together. What do? We create a new M-set, which just is obtained by copying each one of these entries into the M-set here. And how we actually do that? Well, it's not prescribed. We can do that in a number of different ways. This thing here is essentially unordered. We're writing it in an unordered way, but it's not really essential. So we could take these ones and circle 1, 1, 1, and then say mark, 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 and then mark, and then mark, 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 mark. We're just jumping out the contents of these three into a new box. Conceptually, I want you to think about having boxes, having a number of people just upending their containers and everything dropping into a box. So there's the arithmetical analog of dumping the contents of several boxes into a new box. Now, with this naive, almost physical understanding of how we add multi-sets, in this case add numbers, natural numbers, we note that the commutativity and associativity properties of addition are essentially obvious here. Because we're only dealing with something, a situation where order is unimportant, and the only objects that we have, in fact, not a variety of course, we just have these unit marks. That's all that ever appears in our natural numbers. They're all the same. Then the commutativity and associativity are really obvious. In other words, you've got a bunch of primary school students, and you've got them practicing dropping multi-sets of, let's say, just coins of one type. Let's say, 10-cent pieces. So you have a multi-set of 10-cent pieces. Each of the kids has a multi-set of 10-cent pieces, and you're adding all the M-sets together. You have a lot of fun. They would quickly determine that, Jane and Bill combine theirs into a box, and Jane does hers a little bit before Bill, and they look what they get, and then they do it again, and Bill drops his in a little bit before Jane. It's not going to make any difference. Because the order is not important. We have three people, and they kind of dump, and one person gets to dump theirs in first. It's not going to make any difference to the collection. So our students are going to be able to understand that. It's going to be obvious that after a while playing around. So, in particular, in our linear way of writing data, we have this M set, mark, mark, this M set, mark, mark, mark. Then we combine them, we get mark, 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 mark. And that's, of course, the same thing as if we combine mark, mark, mark with mark, mark, mark. We're going to get three of them, and we combine these guys first, and then we add that one. Well, that's going to be the same as if we add the first one to the top of these ones. So even children can be taught this system. And we taught this before they have a language, before they've actually been given names for the numbers. But they don't need to know that this is the number 5, this is number 3, this is number 2. We can just refer to this as the M set, mark, mark, mark. And this is the M set, mark, mark. Maybe use the word units, maybe it's a little bit better word. Unit, unit, unit. This one is unit, unit. So they can deal with things at that level. And they can get a sense of how this number system works, independent of having actually a naming system for numbers. So this is a claim that I'm making for my intuition. I haven't actually gone out and talked to kindergarten system. Maybe somebody could have a go at playing around with the discussion. Maybe somebody has already done this. This is standard kind of educational procedure for very young people. In any case, there's something very simple-minded and, I think, down to earth about this very concrete, simple conceptual framework or approach to arithmetic. Especially as I take this, that these basic properties become essentially obvious facts to even children who are working with such a system. That is what we recommend. Alright, so now let's look at multiplication. How are we going to define multiplication of natural numbers? If we look at the earlier videos in the series, you see that we've defined multiplication there in a somewhat geometrical fashion. Here we are going to stick with a more arithmetical approach. So, to multiply natural numbers, we're going to extend this following multiplication of our unit marks. So mark times mark equals mark. Or if we prefer, units times unit equals unit. We're going to extend that to multiplication of m sets of units. So here's an m set